Hi, my name is Bob Greenyer and I'm a volunteer with the Martin Fleischmann Memorial Project. Today I'd like to talk to you about the new fires a 100 or more year gestation. And this is part one, and it begins with our friend Francesco Piantelli. When we were with him, he got a little bit exasperated at one point. Yes, we were fairly naive and didn't really know all our stuff, and this guy had been living and breathing this for many years. But his frustration came through once when he said simply, "I don't understand why people think they're discovering anything new. Most of this research has been in the literature over the last 100 years and more." To be fair, Piantelli did give us some examples of some things that have been in the literature for many years. And one example that he gave us was the temperatures at which nickel adsorbed loaded hydrogen. And he gave those temperatures as 71 degrees C, 111 degrees C, and 145 degrees C. These are approximate, he said. The first time we used that information was in the glow stick experiment 5.2. That's the one where we saw the so-called signal. And so that in itself is interesting, but whilst this was old information that everyone seemed to be discovering recently, or rediscovering, it was actually in the third quarter, or thereabouts, I think I recall him saying, that this research was done the third quarter century of the 20th century. So it wasn't really something that you could describe as being over 100 years old. So maybe he did say, and it was lost in translation, or I don't know, but none of us seem to recall him actually saying something that was specifically more than 100 years old. Anyway, so I went to, do a bit of online searching as you do, and I went to the Wikipedia entry for cold fusion, which I know is much maligned by some of the people that are interested in this field. However, right at the tail end, the second to last entry in that was this. It's an entry 180 in the sort of references, and it refers to an article by a guy called Fox in 1994 that referenced Canon's patent. Now, I'll provide a presentation that you're seeing here with all the links to the various online documents and annotated documents that I'm discussing in this. But this is, for me, a very, very key piece of information. And the really lovely thing about it is, and you may understand the significance of this, is that it has a patent priority of the 4th of August 1989. And what that means is it expired on the 4th of August 2009. Okay? So, when I was looking at this patent, I was immediately struck by a word I'd not seen used in any of the other research that I had read up to that point. All patent applications, literally anything. And it was on page 2 of the patent, top of the second column, and it was an unusually old English word in the context of LENR. Myself as a native speaker, I wouldn't use this word. And the word is occluding, occluded, occlusion, those kind of variations on that word we used throughout this patent. This is the first incidence of that. Now, I've done a lot of 3D animation, and for me, occlusion means something very specific in 3D rendering, and that is something where if you have a spike like this and you've got a dome of light, the spike won't do much occluding into this crack. But if the spike ends up being like a different shape, they will get more occlusion in the cracks, and you get like a darker area. And it's a method of lighting in 3D rendering terms. So for me, it immediately had significance, this word. significance for two reasons. One, it was an odd word to be using, because quite frankly, people don't use these words in LENR. They use things like absorption, diffusion, loading, etc. Not occlusion. At least that was my experience up to that point. So I did a Google search. I just typed in occlusion of hydrogen gas. And the very first entry, you can do this yourself, is a paper on the occlusion of hydrogen gas by metals, JSTOR. And it had this name, T. Graham, and it had 1867, blah, blah, blah. I thought, 1867? Is that the title of the paper, or is that a date? So I thought, well, okay, let's have a look at this. And I came into my first experience of Thomas Graham, FRS. This guy was born in 1805 and he died in 1869. And he is a British chemist, and he is best known for his work on the diffusion of gases and osmosis, two really, really important processes in modern technology. He has studied specifically in relation to what I'm going to talk about, the occlusion of hydrogen in metals such as palladium and platinum. Okay, so in this paper on the occlusion of hydrogen gas by metals, published in 1868 by the Royal Society, Thomas Graham talks about, he effectively created nanostructured metal deposits and powder by colloidal or precipitation techniques for occlusion of hydrogen experiments. He developed nanoclusters by precipitation of palladium onto platinum wire that then flakes off, yielding highly active platelets. He established the need for negative electrode for hydrogen occlusion, and he established that gas systems occluded less than electrolytic systems, and that occluding material had to be heated and cooled in hydrogen gas to be at all effective. Okay? Like I say, sorry, it's going to be quite a bit text-based, but you can go over this and learn pretty fast. He also established that you need an absolute purity of the metallic surface being essential to the first absorbing action. And these are his words in this paper. Essentially what you're seeing there is he's saying that you need to make sure that the surface of your metal that you want to occlude the hydrogen gas needs to be free of all contaminants. And I hear someone in the back of my head also telling me this, and that person's Francesco Piantelli. And he's not the only one. You'll hear this from Brillouin. You'll hear it from many of the researchers in the field, and this is key pieces of information here. He established that cooled metals held onto their occluded hydrogen even in a vacuum, and that you needed to heat up the occluding material to release the gas. In the case of palladium, you had to heat it up to over 100 degrees C before it would release the hydrogen in deuterium. But actually, I'll come on to that later, because deuterium wasn't even discovered then. So it was just hydrogen. So we knew from our Celani experiments that we could load a piece of wire, it could cool it down, and then you could release pressure from it later by heating it up. What he found out, and it's been in the literature since the 1860s, that if you even put the metal that had occluded the hydrogen into a vacuum for a long period of time, at say 12 degrees centigrade, it did not release its gas, it held on to it. He states that hydrogen cannot be a gas when it is taken into the metal. He's basically saying it can't be a gas when it goes into the metal. It has to be in some other state. He states that gaseous hydrogen can be absorbed at very low pressures into a heated occluding material. And we also discovered this in our early work with Francesco Celani's wire. Moving on, it doesn't end there. Palladium is much better than platinum at absorbing hydrogen under electrolytic conditions. Platinum needed a higher temperature to expel hydrogen. The temperature required to expel the hydrogen so absorbed by platinum was found to be little short of red heat, although the gas had entered the metal at a low temperature. You know what, I don't know why he uses the term red heat. Perhaps it is because he didn't know what the actual temperature, or they didn't have thermometers or means of measuring back then temperatures that were really quite hot. But a little research on the web, and I've given a link there. Red heat at the base level is between 400 and 752. That's visible in the dark, and red heat visible in twilight, 474 to 885. And incidentally, the maximum amount of IR you get from an emitting black body, I think it's also in some literature, it's around about 900 degrees. So these are interesting figures to take on board. More is in this paper. Palladium nanocluster platelets, when heated to 100 degrees C in hydrogen, occluded 982.14 volumes of the occluding material in gas. Essentially, if you think about that, this would mean that 1 cc of platelets would absorb nearly 1 litre of hydrogen gas at approximately 1 bar, because he conducted these experiments at a very little bit over 1 bar. So 1 cc taking on board 1 litre of gas at 1 bar. He calculated this is an approximation of a palladium to hydrogen ratio of 1 to 1. He also says that palladium hydride can be formed, but it is unstable. Is he essentially saying that occluded hydrogen is materially different? And I want people to look into this, because I'm still exploring mentally what this phrase means in the paper. Moving on. So, was Martin Fleischmann, FRS, aware of Thomas Graham, Fellow of the Royal Society? Martin Fleischmann, FRS, was one of the world's leading electrochemists, and so was Thomas Graham. It is therefore inconceivable to me that Martin Fleischmann did not know of and understand the work of Thomas Graham. The observations of Graham would have led researchers, including Martin, to focus on palladium and electrolytic cells due to Graham's discovery that they were a recipe for high occlusion. Only Martin, unlike Graham, would be armed with the knowledge of the existence of deuterium, which was not discovered until 1931 by Harold Urey. I might have got that wrong, sorry, Harold, in your grave, sorry. Which after Chadwick discovered the neutron predicted by Rutherford in 1932, and that led Urey winning the Nobel Prize in 1934. So what I'm saying is, Martin Fleischmann knew about the work of Thomas Graham. Thomas Graham had shown that palladium in nanostructured platelets absorbs very high quantities in gas, and it absorbs in an electrolytic cell, it absorbs more than you can get with the other metals that he assessed. And so naturally for Martin Fleischmann, looking at this, if he was trying to get some sort of interaction between deuterons, he would be looking at palladium and heavy water. Was Professor Francesco Piantelli aware of Thomas Graham, FRS? Thomas Graham, FRS, made one startling prediction when trying to explain how hydrogen could occlude in metals at the density greater than the liquid state. He speculates that the ability of platinum sponge to ignite a jet of hydrogen in air is due to the attraction of platinum for the negative or chlorulous atom of the hydrogen molecule, which attaches the latter to the metal. The process leaves a pair of atoms or a single molecule of hydrogen attached to the platinum. So what he's saying is that you have a molecule of hydrogen, and at some point in its probability distribution of where the electrons are, as it contacts the metal that could occlude it, it's the H minus end. He says here, of course, the negative or chlorus atom is of the hydrogen molecule is H minus. So it's attaching on with the H minus. And then what he's saying is you get two molecules of H2 attached by H minus, and then the oxygen comes along. There's a bit of sea of electrons because you've got a metal there, and the oxygen comes in and takes away the two baseless hydrogen ends. They are just the H plus, and the electrons, I guess, come from the cloud around the metal. And this is how you get, your platinum catalyzer. Basically, you've got your hydrogen coming in, and you've got your oxygen in the air, and it just auto burns it. Okay? This gets me thinking, can we not use, oh dear, catalysts from cars and use what I'm going to tell you a little bit later on in this and the next presentation to create reactors. It is therefore inconceivable to me that Francesco Piantelli would not have incorporated Thomas Graham's work into his understanding of the interaction between hydrogen and nickel. On the one hand, he spoke to us and said that some of this work is more than 100 years old. Well, as far as I can work out, this is basically the key root of this work in 1867, published in 1868. And it specifically hypothesizes with a very testable concept using platinum sponge that it is H minus that's critical to the absorbing process, or in his case, to the occluding process. Were the Cannon researchers aware of Thomas Graham? Firstly, this author, that's me, discovered Thomas Graham FRS by way of seeing for the first time the use of the word occlusion in a LENR paper or patent. So I only got to find out about him because of this unusual word for me in their patent. Secondly, in their patent, they have a phrase that looks remarkably like a summary of Graham's work. And this is a quotation from their patent. Though the amount of hydrogen stored in the hydrogen storage material depends on the species of hydrogen storage materials, hydrogen is occluded in the volume 700 to 1,000 times as large as that of the hydrogen storage material. This proportion corresponds approximately to the volume reduction when hydrogen gas is liquefied. So what I'm saying is, they are basically observing what he said, but almost using his same language with this term occlusion in there. Thirdly, the purpose of the Cannon patent is to devise materials and processes to achieve the same levels of occlusion in a gaseous system as in an electrolytic cell. Essentially, the aim is to create gas state ions that can be then driven into the cathode. Of course, in 1866 to 1867, Thomas Graham did not have the same electrical discharge and control systems available to him that Cannon had in 1989. Given the specific language and the use of that word and its variations, and the text in the patent, it is inconceivable to me that the Cannon patent authors, did not know about Thomas Graham and the limitations of gas phase work. Okay, so in 1994, in New Scientist, I've got a link to this article, Barry Fox, and this is also cited in the Cold Fusion Wikipedia link. He cited, they had a discussion with the authors of the patent, and it says, Cannon's patent, EP 568118, claims new ways to absorb large volume of deuterium in a metal carrier by putting it close to a pair of electrodes to create a gas discharge in the hydrogen-filled chamber. Cold fusion is promoted by cycling the power supply through low and high voltages. The carrier can be a block of magnesium alloy or palladium alloy. For safety, the hydrogen gas is at atmospheric pressure. The pulsed power comes from large capacitors, and the electrodes are shaped to concentrate the electric field. After storing deuterium in a palladium alloy for 60 minutes, says Cannon, the deuterium content had increased with a 10-fold increase of gamma ray emissions after 120 hours. Applying 5-minute cycles of 5 and 500 volts DC for 50 hours produced 20-fold increase in emission. More heat was generated at the negative electrode than the electric energy consumed at the two electrodes. All this, says Cannon, proves that cold fusion works. Nuclear fusion can be occasioned relatively easily, and thus a method for multiplying heat energy capable of generating a sufficiently large quantity of heat energy for practical application, it claims. So, the process in the Cannon patent, I've summarised it here. You create nanostructures on formed hydrogen storage materials using chemical vapour deposition, for instance. You evacuate to remove impurities from the storage material and cell. Sounds a bit like Tom's Brown. You sputter at least once in hydrogen atmosphere to A, remove absorbed materials from the surface, and B, damage the surface to introduce surface defects. That'll sound like a bit that we will come on to a little bit later in the second presentation. The discharge, which can be a spark or a glow discharge, through the hydrogen, which can be a variety of pressures, isotopal mixture, or protium and argon mix. This creates hydrogen ions and hydrogen radicals, including Rydberg hydrogen, that are either positive or polar. A higher voltage gives you a better result, apparently. Apply negative potential pulses of appropriate length to hydrogen storage material to accelerate the activated hydrogen to the storage member. Occlude hydrogen and produce heat. And that's essentially what it's doing. So, beyond that, the patent has expired. This is really exciting. It's expired. Therefore, all of the concepts and all of the embodiments can be openly researched and commercialized. The patent shows effective and a simple way to achieve high levels of occlusion, loading, as we call it these days, into hydrogen storage materials comparable to electrolytic loading, but without the kind of contamination challenges, because there are many issues when you are doing electrolytic loading of materials. Anything that's in the solution or in the vessel that you've got your solution in, it's going to throw those also onto the cathode. And the cathode also gets bubbles built up, and the super wave, one understanding I have of why you have the super wave is that it keeps the surface clean when it's loading. Anyway, the patent claims repeatable emissions of photons, and the patent claims repeatable excess heat production. Moreover, whilst it does suggest some suitable materials and elements, the patent allows for any suitable hydrogen storage material to be used. So whatever stores hydrogen is applicable, and it's not really an amazing thing to discover. It's just another hydrogen storage material that you apply in the same kind of system. Whilst there are some structures defined in the embodiments, the patent allows for any geometry of hydrogen storage material to be used. So it could be a flat plane, it could be, plates, it could be a sphere, it could be a cylinder, whatever. Any structure is valid under this patent. It permits high loading in easily obtainable pressures and temperatures. So we're not asking for extremely low pressures, we're not asking for extremely high pressures. A range of pressures will do. It says in the patent, by repeatedly applying the voltages of -5 and -500 in cycles of about 5 minutes for about 50 hours, about a 20-fold emission of gamma rays was detected against the gamma rays detection of the background. So, here's the reactor. You have the discharge electrodes here, number 23. You have your power supply for the same. You have the reactor structure 22. 26 is your deuterium bottle. It depends on the embodiment. It can be hydrogen in argon, as I said earlier, or a mixture of any isotopes of hydrogen. Here you have your hydrogen storage member. This is just an indicative embodiment with your pulling it down to negative voltage. Here is a pump with your coolant going round, and this assists the loading. And here is a vacuum pump. And that's a very, very simple schematic. So, powder in LENR. Whilst Thomas Graham FRS effectively created nanoclusters, powders and surfaces in hydrogen occlusion research during the 1860s, without specifying them as such, Canon was the first to secure a patent on their use in LENR. In the claim 4 of the Canon patent, it says the apparatus according to any preceding claim wherein either the entirety or the surface of the hydrogen storage member is formed of a hydrogen storage material having a powdery form. So you can have substrate with a powdery form of hydrogen storage material fused onto that substrate, or you can have an entire hydrogen storage member essentially composed of a powdery material. So in the past, I'd given other people credit for being first with powder. Really, without saying it, it should be Thomas Graham, but in terms of patent, it's the Canon patent, which is expired. So, to sum up, there is a patent out there that is based on technology that's more than 100 years old. You will recognise that it looks a bit like Defcanian Green Technologies plasma kind of cell. The other thing is, I told this to Me356 on November the 11th last year. Essentially what I did tell him was, the Canon patent is expired, it's a fertile ground, there's some really good ideas in there that you can work with. I suggest you look into that. And I told him to bear in mind that there are things in the literature, according to Piantelli, that are over 100 years old. Thank you. And thank you also to the US charity, Quantum Heat, Inc., that helped support this video. Coming in part 2, how the expired Canon patent compares to recent Clean Planet patent application. How the expired Canon patent relates to the hypothesized ECAT-X operation. And other patents and papers that fill the gaps. I just want to, here's a little teaser here. This is the image that was released by Andrea Rossi. I've been using image manipulation for very many years, and so I was able to de-noise it. This is what we end up with, this wonderful colour here. And there's the real teaser, the big takeaway, the reveal of this end of this video, other than all of the reveals we've had before in the video, is that if you look at this line here, which is the various gases here you would get in your, what do you call it, neon signs, neon because neon is one of them, yeah. Look at this. This is argon. Now argon's normally blue in your signs, but that's because it has mercury in it. The actual natural colour of argon is this purple colour, which is remarkably similar to the colour in this image. Now, we don't know whether this was doctored in terms of changing the hue, but what we do know is that in the Canon patent, they suggest that if you are using hydrogen with your hydrogen storage member, when I say hydrogen, I actually mean protium rather than deuterium, you should be mixing it with argon in order to get the best effect.